concentration, okay, and the dissociation of gases, or it could be acidic solution, basic solution, like that. So as I discussed a while ago, we have different equilibrium constant expressions. We have Kc, equilibrium constant expression for concentration. We have Ka, equilibrium constant expression for acidic solution, like that. Kb, equilibrium constant expression for basic solution. And we have Kp, equilibrium for partial pressures. Okay, the same rule will be followed. So all concentrations, equilibrium constants will be the concentrations of the product dissociated over the concentration of the reactant. Okay, like that. So all of them goes like that, and each will be raised to the power of the number of moles, both the products and the reactants, for all Kc, Kb, Ke, and Kp, like that. Okay, and then we will be following also the basic method, okay, in getting the equilibrium concentrations. We have the ICE method. It started in I, okay, then in C and E. So I means initial stage, okay, while the equilibrium has not yet been reached, right? And then C for the chemical reactions, and E is the equilibrium of the concentrations, something like that. So ICE. Now, before proceeding to the ICE method or the ICE method, we need to protect, okay, scientifically, the products of our reactants. Okay, reactants meaning the reaction of the reactant. Sometimes it could only be one that dissociated immediately, or sometimes there's an addition between two compound and water, something like that. So that's why there's acidic solution. Any kinds of compounds added will really dissociate it to various species or various products, something like that. Okay, so during dissociation, okay, over not alpha is the degree of dissociation, meaning the number of molecules dissociated of an electrolyte over the total molecules, okay, not yet dissociated, okay, like that, or the total molecules itself alone. So usually the reactant, okay, so the formula of percent dissociation, like that, is equal to the degree of the dissociation times 100. Okay, when we will substitute that mathematical formula of the, then we can have another formula related to that percent of dissociation versus the degree of dissociation. Okay, and then we have also another thing, which is the dissociation factor, which is 1 plus alpha, which is the degree of dissociation, times V minus 1, in which V is the total number of ions, okay, which is the Van 't Hoff factor, something like that. Okay? So meaning to say, if it has a 100% dissociation, our degree of dissociation equal directly to the dissociation factor. That's in the case of a strong electrolyte. You remember our discussion yesterday? If we said strong electrolyte, the alpha is equals to 1, or the degree of dissociation is equal to 1, meaning there's a 100% dissociation. Okay, if it is less than 1, so that is for weak A, example, the acetic acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, something like that, okay? Or it could be the hydroxides, potassium hydroxide, something like this. magnesium hydroxides, and a lot. Okay, I have here um, 4 problems. Okay, I'll just write so that it will not take time for me to write on the spot and then solve on the spot also. It will take longer time for me to do so, and sometimes I will be confused, and my writings will be dirty enough, so I could never do it very properly. Though it is good also to have that on the spot computation, okay, and writing, then it's more better to write clearly, okay, in the bond paper like this. Okay, now we will start now. You can also get your papers, okay, and while I am showing, because we have now the basic concepts and basic theories of this particular topic, which is the equilibrium dissociation of molecules, something like that. Okay, number 1. Question number 1. Okay, this one. I will give you 5 minutes before I will read, and then after that I will also give you 5 minutes showing when I read the problem also. Just take a look first and write down the given data in this problem and try to analyze what is the particular formula will be applicable for this. Okay, and first you need to have the chemical react, then after that write all the data, different variables. It could be temperature, pressure, volume, concentration, and then write also what is being asked, something like that. Okay, and try to analyze the best formula for that. Okay, like that. And then of course, since this is equilibrium of molecules problems, then you have to apply the ice method. Okay, now I will read. Okay, 2.523 grams of hydrogen gas and 200 grams of bromine gas are placed in a 450 ml reaction vessel. Calculate the equilibrium concentration of HBr, meaning hydrobromic acid, in the reaction vessel at 500 Kelvin. The equilibrium constant of the concentration is 400. Okay, something like that. This one. Okay. It's the first step in problem solving, the solution, and then we have to have the data or the given of the particular problem. Okay. It is problem number 1. This is our solution. Okay. It's not the solution, the basic and acidic solution. It's not the other way around the solution. We are referring to the computation or the calculation, something like this. Okay. Solution. Now we have the given. Okay. Okay. In here, it's very clear that there are amounts of reactants stated in this particular problem. Then we must write that down. Okay. So given 2.523 grams of hydrogen gas or H2. Okay. Then 200 grams of bromine gas, Br2. Okay, this one. This is our given. 2.523 grams of hydrogen gas plus 200 grams of bromine gas are placed in a 450 ml reaction vessel. So this means that the hydrogen gas and the bromine gas are being mixed with each other inside the reaction vessel. So it's not stated what kind of reaction vessel. Reaction vessel. So it's not stated what kind of reaction vessel is that. It could be a beaker, it could be a flask, or it could be a bottle. It does not mention. That is important, as long as we know that all of these elements are inside the reaction vessel. And now the volume for this is 450 ml. Okay, volume is 450 ml. So let's calculate first, or already, the in terms of liter. Okay, this is milli. Okay, this milli to move to the left. Okay, milliliter move to the left three times. Okay, like this. So this is automatically 0.450 liter. This is the prefixes, right? I discussed that to you already during our mathematics, basic mathematics live streaming also. Okay, so that is automatically 0.450 liters. Sorry. Okay, like that. Okay, and now there's still another given, the 500 Kelvin temperature of the reaction vessel. So during mixing these two elements, the temperature for this is 500 Kelvin. Okay, like that. Temperature 500 Kelvin. So shall I say temperature of the mixture? Okay. Like that. Now we are asked of the equilibrium constant of the concentration. The equilibrium constant of the concentration, meaning Kc. Okay, like that. So this is our required. Okay, our required is Kc, like this. Okay. So this is the thing that will be able to find out what is the value of the equilibrium constant of the concentration, something like that. Okay, but before anything else, we have also the equilibrium constant of the concentration is 400. Sorry, this Kc is given. Okay, sorry. This Kc is given, which is 400. Okay. So later, required, sorry for that, I beg your apology. The required is the equilibrium concentration, not constant. Okay. Oh my gosh. You should also be well versed to the terms or the terminologies, because there are sometimes you will get confused also. For example, equilibrium concentration, and there's also equilibrium constant concentration. So sometimes you will be messed up. Okay, so better just try to detect and recognize the symbol to make it easier to understand also. Okay, because in here, in this problem, it's not being put into symbol, in which other problems put automatically the case into 400 to symbolic. Kc is equal to 400, but here it's equilibrium concentration constant, something like that. So it confused me with another term above, which is equilibrium concentration. So this is the power again of review. You have to review everything before solving, okay, slowly and gradually, because you will be wrong if you will go back and review the given data. Okay, so this is a tip of advice to everybody, something like that. Okay, so our required, sorry for that, is the equilibrium concentration of HBr, something like this. So in this equilibrium concentration problems, our concentrations are with close and open parentheses. Okay, that would mean equilibrium concentration. So that is being required. How much the hydrobromic, okay, concentration. That is hydrobromic, huh? HBr. The same as HCl, right? Hydrochloric. So it is Br, so bromic. Add IC because that's the rule. So hydrobromic acid. Actually, there's a lot in the family. The iodine family, bromine family, chloride family, fluoride family. So these families are just living in the different, just living in the same apartment, in the same group. This bromine, iodine, fluorine, and chlorine. So these elements have the same charges, which is -1. They react with the positive one, which is the hydrogen or the H plus, neutralize with each other. So through ionic bonding, so it becomes HBr. Okay, no need to discuss that because we already discussed that how it will become HBr, HCl, something like that. It's ionic bond. So it obeys neutralization reaction through their charges, positive and negative. The negatively charged ions and the positively charged ions also. Okay? Like that. So hydrobromic acid. So what is the concentration of hydrobromic acid? Okay, like that. Okay, and we go back to another given, which is Kc, equilibrium constant, okay, which is 400. Okay, so we have now everything here. Okay, so complete already, right? I will show you a little bit in your screen also so that you can clearly see the data, what is being required, blah blah blah. Okay, like that. And now we proceed now to the calculation and computation. Okay, first step. Okay, predict the chemical reaction. So since hydrogen gas plus bromine gas are mixed inside the reaction vessel, so we need to do the symbol for a reaction, Rx and reaction. Okay, that's the symbol of reaction, or simply chemical reaction. Okay, we have the hydrogen gas plus bromine gas. Now we have the reactants. 2, because in the problem it was mentioned that you need to find the molar concentration of hydrobromic acid at equilibrium. So you can easily put that as your product. It's no longer a problem. Okay, but if it is not given in the problem, then you have to predict your own. Okay, so we need to put this H2 plus Br2 is equals to HBr. Okay, for hydrobromic acid. Okay, like that. Okay, now this hydrobromic, okay, is not yet balanced, or this equation is not yet balanced, so we need to balance the chemical reaction. Okay, so left, so hydrogen, 2 atoms. Okay, hydrogen here is nothing, so 0. Okay, like this. Hydrogen is 2 in the reactant and hydrogen is 0 in the product. So in the product there is a deficient number of atoms of hydrogen, which is the coefficient of this hydrogen multiplied by the subscript to get the number of atoms. So put X beside HBr. Okay, like this. Okay, so 2 is equals to X immediately. Okay, because in the law of conservation of mass, it should be equal. So automatically, okay, 2 is equals to X. Okay, in the law of conservation. Okay, now it will become 2. Okay, like that. So we will write the equation so that this will not be dirty. Okay, Br2 is R. Again, you already balanced the hydrogen, and now we need to balance the bromine. Take a look on the reactant, and after that take a look on the product also. So in this visual inspection, okay, we can automatically detect that the bromine is already balanced, but purely visualization, right? Two bromine atoms in the reactant and two bromine atoms in the product. So balance. Again, we write, okay, the, oh, so again, we write H2, which is the balance equation already. You have to rewrite it again. Be sure that it is perfect, okay? You'll never miss anything. So H2 plus Br2 is equal to 2HBr. Take note, you have to be extra careful of your balancing equation because this is very useful in the equilibrium concentration later on when we use the ICE method. Okay, re-inspect if it is really completely balanced, the number of atoms from the reactant compared to the number of atoms of the product. Okay? Malom? Yes, malom. Okay. Like this. We now applying the ICE method. So I means initial. Okay. In this situation, okay, take a look. Okay, so we need to assume or not. Have you asked question? Okay, we cannot assume. Why? Actually, there are amounts of hydrogen gas and bromine gas reacting with each other inside the reaction vessel. So this is totally different from the previous examples because on the previous examples there are no amounts of substances initially are given. So this will trick you also sometimes, okay, like that. And take note, our initial given is not molar concentrations directly. So we need also to think about that. Since that is not a molar concentration directly and it started with the grams, which is mass, then you have to analyze the formula of molarity, which is the molar concentration. Recalling back the colligative property, formula of molarity is equal to moles of solute per liter of solution. Now inspecting the numerator and denominator, moles of solute, we can get the moles of solute because we have the grams of H2 and Br2 initially with the relationship of their molecular weight or their molar masses, right? And then we have also the liters of solution in which 0.450 liter in the reaction vessel. So this will not become a problem already. All we have to do is to compute first before putting in the initial in our ICE method. Because this is not assumption. We have given in the problem. Okay, now we compute one by one first for the number of moles first. Don't worry with the volume, which is the liters of solution, because it is 0.450, which is constant all throughout. Moles of H2. We will be going back there later. Okay? Like this. Solving for number of moles. My gosh. Solving number of moles. I should put n because as I said earlier, the symbol for number of moles is a small letter n. Okay, like that. Solving for n. So first, hydrogen gas. We start with smaller mass. Okay, for first hydrogen gas. Okay, we have 2.523 grams of H2. Then with the relationship of H2 molar mass, okay, or molecular weight, it's gonna be the AMU, the atomic mass unit of hydrogen, or the atomic weight of hydrogen. I am saying atomic weight because it's a single element only. If it is molecules or two or more elements, that will be molecular weight. But if it is only one, that is called atomic weight. Okay, again, if it is a single element, okay, it's still a molar mass with that element, but it is called atomic weight, okay, not molecular weight, because the molecular weight is for two or more elements in a single compound. But still, we can call that both as molar masses, okay? Then another term for atomic weight also is the formula weight. Okay, or it could be the AMU or atomic mass unit. You should be extra careful also with the terminologies. Okay, the AMU, atomic mass unit, the formula unit, or the formula weight, or the atomic weight of hydrogen is 1.008. Okay, like this. So H2 1.008. Since we have 2 H2 multiplied by 2. Okay, like that. So as I told you before, that you should memorize the simpler elements, the most common one, it would be better. But if you don't, it's okay also. Okay, but be sure that the examination will be open book or open handbook, so that you can get the formula weight, atomic weight, molar mass through the periodic table. Because you cannot memorize everything, it's impossible. Okay. So we have 2.016. Okay. 2.016 grams per gram mole. Okay. Actually, our atomic weight of hydrogen gas is 2.016 grams per gram mole. Don't be confused with the grams per gram mole. That is also called grams per mole directly. Don't worry. But other textbooks are expressing that as grams per gram mole. But it could be more better to use grams per mole. Okay? It doesn't matter. Okay? 2.016. Let's go with a more common. Okay, because other textbooks are using the relationship to me, then we make sure that the grams will be cancelled. Okay, so if the grams will be cancelled, gram, so that our purpose is to cancel the grams, and what is left is the mole. Okay, we have to invert. Okay, so grams, mole. Okay, invert. So our 2.016 will be in the denominator, grams, our mole upside. Okay, so that we can cancel the grams. Okay, like this. Cancel the grams of H2. What is left is the moles. We have now the number of moles of H2. So 2.523. If you have the calculator there, you can also solve for the number of moles of hydrogen gas. So 2.523 divided by 2.016 is equal to 1.25 moles of hydrogen gas. Okay? So I have 1.25 moles of hydrogen gas. It's not yet a molar concentration, so divide this to the 0.450 liters, so that it will make this as molar concentration or molarity. Okay, like this. So if we divide this to 0.450, our answer will be, okay, divided by 0.450. So we have 2.78 moles per liter, definitely our molar concentration of hydrogen gas initially inside a reaction vessel, right? So this is 1. Okay, 2.78. 2.78 moles per liter of hydrogen gas. And now we will compute to the bromine. Bromine gas. Number 2. We compute only in order we can solve for the equilibrium concentrations by using the ice method, because we cannot do that without this, because we cannot show, because there's given or there's data in the problem. Unless there's no data, then we can assume that it is 1 initially, but it's not. Okay, like this. Okay, so for bromine, so this will become a hint A for bromine gas. We don't know the atomic weight of bromine. So how can I memorize? Oh my gosh, I think it's gonna be 90 point something. I don't know. Or 70.90, something like that. I don't know. Let's check. Okay. Bromine, 200 grams. Bromine gas, sorry. 200 grams of bromine gas. So, again, the formula weight or the formula atomic weight. Okay. It's equals to 2 times wala patakabaw. Then we have to get that in the periodic table. Okay. Like that. So, it's better that we have the periodic table beside us or in our hands before solving this kind of problems. But for me, I did not prepare that one. So, I have to Google that one in the net. Okay. Because I did not memorize also. Like that. Oh. Molar mass of bromine. Of bromine. Like this. Bromine atomic weight. Like this. It will not show. Wait, I found it difficult. It's not here. Bromine. So, atomic mass unit. We use all the terms in order we can get that in the Google Chrome. Atomic mass unit of bromine. Like this. Okay. Wait for a while, because we need to get the atomic weight of bromine, but it's not yet here. Let's say, because we don't have the periodic table. Okay. Okay. Bromine. What's that atomic weight, right? Bromine. Weak signal. Bromine. Bromine. 79.904. Okay. 79.904. 79.904 is the atomic weight of bromine. Okay. So, like that. Sorry. Wait for a while. exposed for a while. So the atomic weight of bromine is 79.904 times 2. Okay. 7.904 times 2 is equals to 159.808. 159.808 grams per mole. Okay, this one. Molecular weight of bromine is 159.808 grams per mole. Okay, and then we will solve for the number of moles. 100 grams of bromine gas times the reverse of this molar mass or the atomic weight, so that we can cancel again the grams. Okay. So our moles will be 200 divided by 159.808. 1.25. Oh my god! 1.25 moles of bromine is just the same with the hydrogen gas. Take a look. Our number of moles of bromine gas is equal to the number of moles of hydrogen gas. So if we take the molar concentration, so it's just the same, right? 2.78. Moles or letter of bromine. So we have now the molar concentrations of hydrogen gas and bromine gas, which are equal. 2.78 moles per liter, and then this 2.78 moles per liter will be our 2.78 molar or capital M. Okay, like the equation like this. We now put that values we obtained from our computation. Okay, so we need to, our initial will be 2.78 H2. We put now because that's initial. Okay. And also bromine is 2.78. How about the high? Okay, since if it's, sorry for my tongue, if it was not mentioned in the problem, then we leave this as 0 initially. Okay, like that. Not let, but it's in reality it's 0 because nothing. Okay, 0. And now we go to the C, change. Since H2 and Br2 will give the molar concentration to HBr, then it will be minus or negative X, because we let X as the molar concentration during the changes. Okay, this is minus X. Okay, minus X and minus X. Now in the hydrobromic acid, since it will receive, okay, the molar concentration of H2 and Br2, that is positive X or plus X, because again we let X as the molar concentration during changes. Okay, because he received, that means X plus. Okay, like this. So that is our C, changes of the changes minus X plus X. And now we go to the equilibrium concentrations, which is the most important of all. Okay, for the reactants, for H2, our equilibrium will be equal now to 2.78 minus X is equal to 0, because at equilibrium it must be equal to 0, neutralization reaction. So this will be 2.78 minus X. And also 2.78 minus X for H2, because they have the same molar concentration. So 2.78 minus X, 2.78 minus X. Okay? And then how about the hydrobromic acid? The hydrobromic. Okay? This is only X. Because I will show you why. because this is 0 plus x, okay, is equals to 0, okay, and then 0 will be cancelled. Okay, equilibrium, 0 plus x is equals to 0. Mathematical expression or any computation in the whole wide universe is just the same. If you will carry that, no carry is just the same, unless it is negative, you should carry that one. But if it is not, if it is positive, no need to carry that plus. It's understood to be nothing on the side of that particular figure or variable. Okay, so it's just x. Okay, not plus x, because it's negligible. The sign will be negligible because it's already positive, right? So now we go to the equilibrium concentration constant, Kc. The formula of Kc, okay, will be equal to the concentrations product. This time it's the reverse, because normally in a problem solving it starts with a reactant, which is originally a compound, acidic solution or basic solution, but this time starting with two elements and it gives off the compound. So this is a synthesis or combination reaction, right? In my discussion of the type of chemical reactions, because you clipped and you add two elements to produce one compound in the product. Okay, our equilibrium constant expression case is equal to the HBr, concentration of HBr. Okay. Okay, let's review so that we will not be wrong. Okay. I won discussion, but it's better to review. Okay. So 0. This personally me also, I take the review also after solving. Okay, during the chemical engineering board examination, after I solve and I have to review it. Okay, like that. It's an SOP, a rule after solving the problems. Okay, so we can apply here also in discussion or in the actual examination. Okay, that's what do you call the one? SOP, standard operating procedure, that after solving you need to review. Okay, we will review this one. Dice method. 2.78, 2.78, and 0. And then it changes. Negative x plus x. Oh, sorry. There is 2x. Okay, sorry. See? Very important. Okay, so this is 2x. See? So I almost got wrong. When I did not review, I will be wrong. Like this. Okay? For intelligent people or smart people or clever people, they don't have to review because they are very high IQ. But for us, average IQ, like this, okay, we need to review. Okay? So that's 2x. Okay, now if it is 2 raised to the power 2, the concentration of hydrobromic acid raised to the power 2, because it's stated in the equilibrium equal to equilibrium expression. For HBr, that is 2x. Substitute. Okay, 2x. And then 2.7 times 2.78 minus x for the bromine gas. But we have Kz in our given, right? Equilibrium constant expression here. Okay, 400. We need to put this 400 in our equilibrium constant expression formula. Okay, so 400. Like this. Do the mathematical operation and you can solve for the x. Do the mathematical operation and you can solve for the x, which is the molar concentration in the equilibrium stage. Let's solve it. But again, in mathematics and in algebra, before going further, you must simplify first your calculation before you going to do the factoring method, quadratic equation, blah blah blah, so and so. We need to simplify first what is being simplified at that moment. If there's no simplification will be done, this is already simplified, of course, then do it directly. But if there are still things to be simplified, simplify it so that it will not become complicated somewhere along the way of your calculation and computation, something like that. Okay? So in here, 2.78 minus x is the same as 2.78x of H2 and I2. So we need to put that as 2.78 minus x raised to the power 2. It's just the same. Okay? Like that. So those who are good in mathematics will be at an advantage here, somewhere in the part here. Okay? Because they can easily simplify. Okay? Right? See? So it will now become 2x raised to the power of 2 and 2.78 minus x raised to the power 2 is equal to 400. Now simplify by multiplying by 1/2 each side. Algebraic rule or expression. Multiply each side by 1/2 so that it will be cancelled with the 2 exponent. Okay, 2 times 1/2, the 2 will be cancelled, so nothing will be left. So, okay, multiply with 1/2. Okay, so 1/2, so 400, square root of 400, let's take this way. Okay, so square root of 400, meaning square root. Exponential 1/3 automatically being cube root. Exponential 1/4 automatically 4th root. Exponential 1/5 automatically 5th root, 6th root, 7th root, 8th root, so on and so forth, infinity. Okay? Like this, so 400 square root is equals to 2x the 1/2 to the exponents of the reactants and the product. So what is left is a simpler one. Chemistry problem, but it involves also algebraic expression. Okay? So square root of 400, it is very easy to do it, even without calculator, because it is a perfect number. So 20 times 20, that is 400, right? But if it is not perfect, you have to get your scientific calculator for that. Okay, so this is a perfect square root, so this is 20 immediately. So 20 is equals to 2x. Okay, and then 2.78 minus x. So this is now very simplified, this one. So 2x, 2.78 minus x. Solve for the value of x. Press cross, something like that, okay? You can do by yourself. All students, including me, will be, in error at that part. And then if you proceed further, your molar concentration should be wrong. Most or majority, because that part is an analysis. Okay? Initial concentration, changes of the concentration, and equilibrium concentrations. It's easy to memorize, but that part is analysis. That's why it's difficult. Like this. Okay, I solved mathematical. We'll show you later. So 20 times 2.78 is equals to 55.6. 20 times 2.78, okay. Then minus 20, and reverse this one, but we still need to make it proper because like this. So 2x transpose, negative transpose to the right will become, to the left will become positive, right? So 20x 55.6. Be careful also with transposing, it matters a lot also. Most it will make you in error. So do it carefully, systematically, and then review before going to the final stages. Because if you read time and you have to re-review all, but if you review the most important part, especially the analysis part here, which is the ice here, the concentrations. That's what I did, right? I re-reviewed the analysis parts, which is the ice. Then it is worth while, worth saving for your time. Okay, like that. So 55.6 divided by 22. So X will be 2.52. Okay. So we have a concentration of X at equilibrium which is 2.52 molar. Okay. We solve the value of X, which is our molar 0.53 or 2.527. Let's say 2.527. Okay. Since we are asked, we go back to the problem. We already have the X. Since we are going to find the HBr, our required is HBr, molar concentration of HBr. So recall the analysis ice method to the equilibrium concentration. Go to the HBr. The HBr is 2x, right? We are not asked by H2 and I2. Our problem asked for what is the equilibrium concentration of hydrobromic acid, like this. So go to the equilibrium, which is 2x, then substitute the 2.527 and bingo, you can get the answer here. Okay, 2 times 2.527 like this times 2. So we have 5.05 molar of hydro. So 2 times X in the equilibrium of the hydrobromic acid. So we have now 2 times X or 2 times 2.527. We have 5.05 molar or moles per liter of HBr in the equilibrium state of HBr. Then if the problem also has a follow-up questions regarding what is the equilibrium concentration of I2 and H2 also, and you have to do this 2.78 minus X, so 2.78 minus 2.52, and the answer will be the same as I2, like that. But the problem is only asking for HBr. And then if the question there is multiple choice, then you have to do it one by one, which is correct then in the choices. Okay, like that. Then if it is not really found your answer there, then you have to review. Okay, but if it's more closer, there's an answer because that is time pressure. Okay, for example, the choices are having, let's say 5.01, and your answer is 5.05. That is more closer, right? You don't have to review again because 5 is more closer, only decimal point. Because the choices are also very far. For example, the choices are very far. So 4.8, 3.7, and 5.01, like this. But your answer is 5.05. But if the choices are very near with each other, you have to recompute. For example, you got the answer of 5.01, and the choice is 5.0. The points must be perfect. Okay, the decimal points must be perfect. Then rewrite it again. You cannot guess your answer. Then recalculate it again, and then you get the exact on the choices, and that will be your answer. Okay, like that. So that's the technique also in solving problems, especially in examinations, actual examinations, but it's time pressure. Okay, like that. So we answered now the problem. Okay. So again, this one. Read it again. Okay, like this. Okay. 2.523 grams of hydrogen gas and 200 grams of bromine gas are placed in a 450 ml reaction vessel. Calculate the equilibrium concentration of HBr in the reaction vessel at 500 Kelvin. The equilibrium constant of the concentration is 400. So, the equilibrium concentration of HBr is 5.05 molar. That's our final answer. But take note of the problem. What variable is irrelevant? Irrelevant. The temperature is irrelevant in this problem. Temperature is not necessary to compute the answer, okay, for this molar concentration. So it adds confusion only. Okay, because some students will also use the maybe the Avogadro law like this, because they see already that the temperature is there, or the PV and RT because there's a temperature like this, or the Gay-Lussac's, Charles law, something like that, or the Henry's law, Ryle's law. There's a temperature involved like this, or the colligative properties, freezing point depression, boiling point elevation. Okay, vapor pressure lowering, and the osmosis, something like that. Okay, so do not force to use the variable just to solve what is being required. Sometimes it's already a decoration, something like this, on the problem. Even though there are still so many, and then it's not used. That's the more confusion in the problem solving, really. Okay, headache. Even up to now, that's my headache also. Because it tends to confuse us that we need to force to use that. We need to incorporate that so that we can achieve the real answer. But the more it will confuse us, and the more it will take time for us to analyze. So, okay, like this. Just take note for that. Okay, especially in equilibrium concentration. Okay, it's stated there that temperature, right? Temperature is the factors, right? Remember, as what I discussed yesterday, that the four factors of the degree of dissociation affecting, see, factors, four factors affecting of the degree of dissociation to this topic, right? So it's stated there at number 4, temperature. Okay, affecting. Then why it doesn't affect in our problem solving? Okay, so and then if it really affects the degree of dissociation, then we need to force them to use this in this problem, because that is factors affecting, right? Sometimes like that, we will be puzzled. Okay, but we need to think that the temperature is not necessary in this particular problem. Okay, only the molar concentrations and pressures. We should only remember the equilibrium constant expression Kp, Kc, Ka, and Kb. There's no Kt. There's no equilibrium concentration temperature. No. In fact, there's no also Kv volume. No. Okay? It's only the pressure and the concentration. Take that in your mind. Okay, so that means the temperature will be irrelevant in the particular situation. Okay? Like this. Though it's necessary in the problem, because at that 500, okay, the Kz will be like this. Okay? Okay? But you can put already Kz, no problem, because when you put Kz already in the problem, that means at that temperature, you need to put temperature. Okay? Because you already putting the Kz. What's the use of temperature? Okay? Like that. But that's only confusing the students. Okay? Remember that Kc, Kp, Ke, and Kb, temperature is not involved in the equilibrium constant expression. There's no Kt. Okay? But temperature is one of the factors that affecting the degree of dissociation in the actual movement of gases H2 plus Br2 like this in the actual scenario. But in the calculation, no need. Okay? You know what I mean? Okay? Like that. Because H2 particles and H2 particles reacting with each other like this and produces like this HBr. So the temperature there matters, because the more the high the temperature, the more it will bombard with each other. You know, they will react with each other if it is very high temperature, something like that. In exothermic reaction. So the particles of gases will be busy enough to collide with each other. So that the solubility is higher at a higher temperature, something like that. In exothermic reaction. So that's what it means there as the temperature, as the factors that affecting the degree of dissociation. It's not really on the factor in the calculation, in the computation, something like this. Okay? Very clear. Thank you so much for that. Okay. That is problem number 1. Oh my gosh. And now we go to problem number 2. What's this? Oh my gosh. I will read first. 2 molar of I2 plus 2 molar of bromine 2. Yes, we have already the atomic weight of bromine. Okay. are initially present in a reaction mixture. Calculate the equilibrium concentration of I2, Br2, and IBr at 45 K. Equilibrium constant of the concentration is 100, like this. Okay, take a look, 5 minutes. So write down the data in your solution and then what is being required. Okay, and then balance the chemical reactions. Predict first the products from the reactant, something like that. Balance the chemical reaction before applying the ice method. Okay, like this. Okay, very clear. Okay. Okay, let's solve now. We don't have to be systematic already. We will go directly to the ice method, huh? Because, you know, it's just the same story. Okay? So, that's only the purpose to make us understand well or properly. That's why we need to systematize our discussion in an organized fashion. Okay, but now we will go directly to the ice method. First, the reaction, balance the chemical reaction, ice method, and the equilibrium constant expression. Okay? Like this. My gosh. Oh! Ganon. Okay. I2 plus Br2. This is our equation. Problem number 2. My gosh, what's happening? Okay, problem number 2. I reaction Rxn. I2 plus Br2. This one. Iodine gas plus bromine gas is equals to iodine bromide. Okay. There's no subscript for this IBR because both of them having one. Okay? Like that. Having one charges, something like this. Okay? So balance the chemical equation. I2 for iodine. I2 and then in the product nothing. So 2 is equals to X. So put 2 in the IBR like this. So I2 plus Br2 is equals to 2 IBR. Like this. I2 plus Br2 equals 2 IBR. Balance the equation. In this situation, we balance one of them, automatically it will be balanced. Because it's easy to balance the chemical equation if it is diatomic molecule, especially the iodine and bromine. Okay, these are diatomic molecule, something like this, or diatomic element. Okay, it's balanced, right? We inspect again. I2, 2I, Br2. Okay, perfect. If it is not balanced, then it will be a problem in the ice method. Okay, like this. Ice method, initial, go. I2, it's being mentioned that there is 2 molar. Okay, so it's 2. Bromine, 2 also. Okay. Our IBR is nothing in the initial. That's 0. Okay, so 2 molar each of I2 and Br2, but IBR nothing, so initially 0. Okay, and then changes. So let X as the molar concentration of the reactants of the product. So 2 minus X, sorry, minus X. And then here, minus X, minus X, minus X, okay? Because there's no number of coefficient beside I2 and BR2, okay? Like that. If there is, then you have to, for example, if there is a coefficient in I2 which is 3, then you need to put minus 3x, like that. But no, that is positive 2x, because the reaction will favor to the right, basing on the Le Chatelier's principle. Okay, if the products loses the energy, specifically its concentration, the reaction will shift to the right, okay, to reduce the stress of the reactants, and it will be given to the product. My gosh. Okay, to give the burden to the product, something like this, or a stress, because Le Chatelier's principle number 1 means whenever a stress is applied to a system of equilibrium, the equilibrium will shift in such a way to reduce the stress. To reduce the stress, he will give, I2 and BR2 will give the molar concentrations to the IBR. That's why it's become positive 2x like this. So obeying Le Chatelier's principle. Okay? Equilibrium. Okay? In the equilibrium, so that would be equal now to 2 minus x, both I2 and BR2. Or you can say 2 minus x is equal to 0. But since 0 is nothing, you can just write 2 minus x. Okay? Each, because the same, 2 molar concentrations initially. Okay? But our 2IBR will become 2x. The plus sign is removed because it's irrelevant. Okay? Because if there's no sign again, that would mean positive. Okay, like this. And now, equilibrium constant expression. Okay? Kc. Ganon. Kc, so IBR, which is the concentration of the product, raised to the power 2, because there's a coefficient 2, and you have to raise that in the exponent. Charot. Like that. And then I2 BR2. Okay. Our equilibrium constant expression will be IBR raised to the power 2 over I2 and BR2. Now substitute the equilibrium concentrations, those that involving X. Okay? Substitute that immediately. Okay. And our Kz also is given, so don't you worry, like this. So we can solve it. So Kz is 100. IBR is 2x in the equilibrium concentration. 2x raised to the power 2 charots. I2, 2 minus x. And BR2 is 2 minus x also. So we can rewrite this as 2 minus x raised to the power 2. Okay, like this. Take a look. Algebraic expression. Basically, the same as the number 1 problem, right? There's a little bit changes, but the concept behind is just the same with problem number 1. But in this problem, there's no given of masses. Okay? Okay. Perform mathematically, charots. Okay? Like this. Write that as 100 equals to 2 2x raised to the power 2 and 2x raised to the power 2, and then multiply each side to 1/2. Square root of, so this one cancels out, and then 2 minus x is 1. Okay, right? Substitute only. Plug in to the equilibrium constant expression formula. Okay, like that. Okay. Square root of 110 is perfect square. We will be very lucky if the problem will give us a perfect KC, meaning say 100, 200, say 900, because the square root is perfect. But there are times that they will not give like this. For example, 1.3 times 10 to the negative 8, like this, the equilibrium constant, that will be more tasky to solve. And you'll be employing most of the exponential. We will end up with quadratic equation, you know, like that, because it involves x. Okay, so like that. So minus b plus and minus square root of b squared minus 4ac over 2a, and a, b, c are the constants, something like that. Okay, or you can use the factoring, but I prefer the quadratic equation. Okay, so 2x, 2 minus x, 20 minus 10x is equals to 2x. Okay, 20 minus 10x minus 2x is equals to 0, and then 12x is equals to negative 20. So what cancels negative? X is equals to 20 over 12. 20 divided by 12. 20 divided by 12, 1.67. Okay, like that. Our molar concentration X is equal to 1.67 molar. Okay, this one. Solve for the value of X using our molar concentration is equal to 1.67. Okay, and then since the problem asking for calculate the equilibrium concentration of I2, BR2, and IBR. So I2, we're going back to the I2. So the I2 is 2 minus X. Equilibrium. So 2 minus X, therefore 2 minus 1.67, 0.33 molar. So equal I2 automatically equal to BR2. No need to solve because we have the same expression in equilibrium. So 0.33. Okay, and then for the IBR, 2x. IBR, 2x, or 2 times 1.67 molar is equals to 2 times 1.67 molar, 3.34. So our answers, the final answers will be molar concentration of I2 is concentration expression in E cash 2 times X in the equilibrium concentration. So 2 times 1.67, so 3.34. Okay, so these are the answers. We have 3 answers because 3 required, or 3 molar. Okay, like that. Again, molar concentration of I2 is 0.33, BR2 0.33, and IBR is 3.34, like this. Okay, that is problem number 2. And we go now to problem number 3. Problem number 3. Okay? Take a look with this one. Problem number 2. We have still 2 more problems to solve. Okay? Number 3. Problem number 3. Okay, I will read now. A reaction mixture contains 0.75 molar of HI. At equilibrium, the concentration of I2 was found to be the equilibrium concentration of HI in the mixture. Looking for the equilibrium constant of the mixture. Okay. Let's go directly to the formula of equilibrium constant expression, because we know already how to do our solution systematically. Then we need to go direct. Okay. Because it's just the same manner. Okay, like this. So we have reaction first, remember, okay? Always starts with a reaction, of course. Chemistry is just like that. You always starts with the chemical reaction. Balance the chemical reaction, you can solve everything now after that. Okay, like this. So, HI first. What is HI? Hydroiodic acid. Same as hydrochloric acid. Because iodine, bromine, fluorine, chlorine, okay, belongs in the same group in the periodic table. Or in short, they are living in the same apartment. So, they have same charge, which is -1. Okay, and then for the hydrogen, positive, then react. Positive plus negative is equal to 0, ionic bonding. So it will become now a compound called hydroiodic. Okay, like this. Each I will produce H2I2. You will be wondering why always two like this, because that is the rule. They will exist the atomic element when it splits to the product. There's no I3 like this. There's no H3. I remember there's H3O, hydronium ion, right, in a solution. When you add, for example, if you add a basic compound to water, you can produce H3O, something like hydronium ion. But there's no such as H3. Okay, but let's review that, because in nuclear chemistry also there's what we call as deuterium, like this. As far as I can remember, deuterium, tritium, like this. And I doubt hydrogen has an isotope, exists in isotopic form, based on my memory, something like this. But I don't think so. Even though there's an isotopic like that, but still they will not exist in the products as H3, H4, like that. Normally it's always H2 in the product as a diatomic, because this is the most stable form of hydrogen, granting that there is another form of hydrogen in its isotopic form. You know isotope? Okay? I think elements that have the same atomic number, like this, but different in their mass numbers. That's the definition of isotopes as far as I could remember. Okay, just review that by your own. Correct me if I'm wrong. The same atomic numbers, but differ in their mass numbers. Okay, like that. Not really sure. Okay. Okay, I think so. But iodine, other than hydrogen, iodine, fluorine, bromine always exists as I2. Two, the atomic number. But still we need to research this H2, because I'm not really sure if it exists as H3, H4, like this. I remembered only in the nuclear chemistry that there is deuterium and tritium for hydrogen. Okay, like that. But I'm not really sure also. That was 20 years ago. Okay, going back to the chemical reaction HI, hydroiodic, to produce hydrogen gas plus iodine gas or iodine gas. Okay, like iodine gas. Okay, balance the chemical equation. Go. Inspect visually. Hydrogen 2, like this. You put hydrogen 2 here. Balance immediately. Okay. 2 moles of hydroiodic, okay, solution or mixture to produce hydrogen gas plus I2 gas. Okay, it is expected that in this reaction vessel, it is not closed vessel, right? So that they will release to the atmosphere to produce H2. Okay? Like that. Okay. And then at equilibrium, the concentration of I2 was found to be 0.300 N. Oh, at equilibrium, I2 was found to be 0.3 Kc. Our problem is Kc. Okay, equilibrium constant of the concentration. So Kz will be the concentration of H2 multiplied the concentration of I2, okay, over the concentration of HI raised to the power 2, because there is coefficient like this. Okay. Kc, equilibrium constant expression of the concentration, will be equal to the concentration of the product over the concentration of the reactant, since it will be raised to the power 2. Okay, like that. And now we go now to the ice method, because we are now declaring that our chemical equation are already balanced completely. Okay. And we need to draw a table. Okay. Like this. I, initial. C, change. T, equilibrium. So ice will be important in equilibrium. Okay? You know? The solid phase of water. Okay, that's ice. Okay. HI. It's mentioned in the problem? No, it's not. There's no. Wait. A reaction which you have 0.75. I get sleepy. Okay. There's an initial of 0.75. Sorry. See, you have to take extra careful in the analysis of ice. I told you. Okay. H2 is mentioned, nothing, so that's 0. I2 is mentioned, half, 0.30. No, concentration was not even, no, 0 still. Okay. Our initial will be like this. I, 0.75 molar of HI, 0 for, okay, H2, and 0 for I2. For our changes, okay, let X is the molar concentrations in both reactants and products. We have 2HI, so meaning to say negative 2X. Okay, you multiply the number of moles to the molar concentration that we assume as X. So 2 times X. Negative meaning to say initially this HI will give to H1I2. That's why it will become negative. So minus 2X. Okay? Normally when you give something, you will gain a thing. Okay? That's the philosophy there. If I have 10 pesos and I will give the 10 pesos to my brother, I have negative left. Nothing. Okay? Something like that. So it's always negative in my pocket. That's the philosophy there. Okay? So, H1I2 will receive, so it is positive X and positive X. Equilibrium is mentioned in the problem. There's an equilibrium concentration of HI, nothing. Okay. So that is 0.75 minus 2x. Okay. And then for H2, have nothing also. So that is plus x. I2 have equilibrium concentration. It's there in the problem. At equilibrium, the concentration of I2 was found to be 0.300 molar. So you have to put 0.30 molar, not x here. Okay, because it's stated in the problem. The equilibrium, the concentration of I2 was found to be 0.300 molar, to have. So, meaning to say, x is equal to 0.3000 molar. Why I put x is equal to 0.3000 molar? Because again, law of conservation of mass, that you have to equate. I let x as the molar concentration of the products and reactants, and then this law conservation of mass, it is equal, right? So x is equal to 0.300 molar at equilibrium, like this. So we have already the x, okay? No need to put on the a detailed one and very complicated. So we have the x now here, huh? Okay. Kz, substitute in the Kz now. Going back to the Kz. H2, okay, ganon. X. Okay. Which is 0.300. And you will ask me, sir, why did you put 0.300 M for H2? That was for I2 only. No, but take note for the chemical reaction. I2 and H2 have the same behavior, right? They have the same behavior, at the same time, they have the same number of moles. Their characteristics and their properties are all equal. So will it act as molar concentration in the equilibrium? So will it also act as the molar concentration of I2? Then automatically the value of I2 will be also the value of H2 by analysis. Though it was not mentioned in the problem. But by analysis, they should be equal. Okay? Like that. So I should also put 0.300. Okay? So 0.3. Okay? And then our HI raised to the power 2. Take a look at this formula. This is our Kc. Our HI raised to the power 2. What is our HI in the equilibrium? It's here. Right? It's here. So, 0.75 minus 2x. Okay. Now, 0.75 minus 2x. But we have the value of x. We can immediately substitute that 0.300 m also directly for HI, right? Okay, so we need to substitute now. So, this is 0.300 raised and then 0.75 2 minus 0.300 like this. This is our final. We can get our Kz now. Okay, so 0.3 Kz is equal to 0.300 times 0.300 over like this. Okay, concentration which is 0.75 minus 2x. So 2x, 2 times 0.300 molar. Okay, for x, because we already solved the x in the equilibrium concentration above in our ICE method. Okay, now we can compute for the Kz, which is being asked on the problem. Okay, like this. Mathematics using calculator. Okay. My gosh. So 0.300 times 0.300 is equals to 0.09. My gosh. And then 2 times 0.300, 0.6, 0.75. Okay, 0.75 minus 0.6, 0.15. 0.09 divided by 15. 0.6. Oh, perfect. Oh my gosh. Our KZ, which is being asked, equilibrium constant of the mixture or concentration will be equal to 0.6. So that's our answer for the problem. Calculate the equilibrium concentration of each in the mixture. Our answer is 0.6 molar. Okay, like that. So in equilibrium concentration computations in chemistry, in this topic, in the equilibrium concentration expression, our clue will be there always, the word equilibrium. Okay, if there's no word equilibrium, that is not equilibrium concentrations, of course. Okay, remember the word equilibrium, like that. If there's no equilibrium, so that problem is not related to equilibrium dissociation of molecules, right? Something like that. It's our first, for example, the chemical engineering board examination. This will be rumbled with other problems also. All will be rumbled and you will be confused. This will be rumbled to ideal gas law, Rayleigh law, Henry's law, like this, Avogadro's law, Charles' law, Gay-Lussac's law, Dalton's law, partial pressure, okay, combined gas law, van der Waals of real gases, colligative properties, blah blah blah. Okay, so you will be confused if you will not take down the K points or K terms in the problems. Makes you confused. Okay, especially when this makes you confused. Okay, especially when this problem are added with temperature and pressure like this, and temperature and pressure is not important in the equilibrium during the calculation. It can affect the degree of dissociation, but for the calculation it doesn't matter. Something like that. Okay. So we have still another problem, last problem. Oh my gosh! Very lengthy discussion of this equilibrium dissociation of molecules problem solving. Oh my gosh! I'm enjoying. Are you enjoying, guys? Oh my gosh. Like this. Now we will take consideration on the differences. In colligative properties, okay, it is dependent on the particles of the solute, okay, in a given solvent within the solution. So, the nature of the solute, the identity of the solute, the nature of the solvent, and the identity of the solvent also, the temperature, the concentration are not the factors affecting it. Okay? It's very clear. Only particles, like an ions or molecules. But here in the equilibrium, the concentrations will really matters. Okay? The identity, the nature, the behavior, the molar concentrations, blah, 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 so on, so. Okay, there's a difference. Okay? And there also, in the colligative properties, we assumed always, I think so, unless it's specified in the problem, that the degree of dissociation is always 1. Meaning, the percent of dissociation is always 100%. Meaning, the molecules are dissociating 100% in a perfect behavior. Okay, like this. That's why you can automatically predict that your Van 't Hoff factor, which is the I, small letter I, right, will be equal automatically to the dissociation factor. But in the case of equilibrium, the story is not like that. The degree of dissociation is not always 1. It's always, not always 100%. Okay? Like that. It could be lesser, the degree of the dissociation, which is alpha. It could be lesser always. Okay? Because if our degree of dissociation will be equal to 1, so that's strong electrolytes already. Okay? So that's why in colligative property, we are trying to solve strong electrolytes there. Okay? So even if the percent dissociation are not mentioned, it's not specified there, that it's 100%, that is automatic by theory. Okay, that the degree of dissociation alpha is equal to 1 and the percent of dissociation is equal to 100% B. Okay, here in the equilibrium concentration mixtures, we are not dealing of 100% dissociation on alpha, which is 1, or degree of dissociation is 1, because we solve more on the weak electrolytes, not on the strong electrolytes, or else the degree of dissociation is equals to 1. No need to go farther, because we know already the degree of dissociation that is 100%, right? What's the purpose? Okay? So meaning here, it's not a perfect behavior of dissociation. That's why it matters in the amount of the molar concentration. Okay, there are factors affecting the degree of dissociation. But there in the colligative properties topics, with the vapor pressure lowering, boiling point elevation, freezing point depression, and the osmosis or the osmotic pressure and the vapor pressure lowering. Okay, it's different story here. Okay. The only problem is when the examination mixed the colligative property and this equilibrium. That's a very headache. Alright, because there are instances like that, especially in most chemical engineering, problem solving, that they will try to mix everything and you'll be confused what to do first. Okay, and we will be confused, especially for the higher chemistry, something like the physical chemistry, like this, the unit operations, like blah blah blah, so on and so on. Oh my gosh, it will become a headache. Okay, for that. So next week, oh my gosh, kung pa na-solve lahat, di ba? May number 4 pa. Next week we will be oh my gosh, what's that? Our topic will be just not really that long or lengthy, because we will be talking on the periodic table. Okay, the behavior, the characteristics. Oh my gosh, what's happening? Sorry. The relationship between the electron affinity, the electronegativity of the elements, like this, the radius of the atomic radius of the element. For example, if this element have a high electron affinity, would it affect the atomic radius as we go from the left to the right in the periodic table? See, like this. And then what will happen to the electronegativity if the electron affinity will increase from the top to the bottom of the group or of the family of this periodic table, like that, and you have to analyze something like that. So this is the question that states in for example, which is more heavy, bromine or iodine? Only that question, and you need to answer that one, because that's referring to the periodic table. If you don't have an idea, you cannot know where is the more heavier. So if we speak about heavier, that's referring to the molar mass or the molecular weight. Okay, automatically. If you don't have an idea, you cannot answer that question. Okay, which is more heavier, an oxygen or the hydrogen? There's no figure given in the question, but by theory, that's referring to the atomic weight or the AMU, atomic mass unit, something like that. Okay, and in the next topic also we will be discussing also how to compute the mass number, the atomic number, like that. Okay, and then the relationships, as I said earlier, electronegativity, electron affinity, atomic radius, blah blah blah, so on. So okay, the topic is not really lengthy because it's talking about relationships only, not solving too much. There's a solving, but it's only basic mathematics, plus minus only. Okay, regarding the what is the mass number of uranium, like that. If you already know the atomic number, and you can get the mass number of uranium, something like that. Okay, that's why in a periodic table, it will is the heaviest in the periodic table. Okay, it's only changing the word, but it's the same. So the students will be confused anymore, because the question is not on the periodic table. The question is, which is the most heaviest element in the universe? Imagine universe. Okay, and you can answer already, because the word universe replaces the word periodic table, but actually it's just the same. It's already theory. The heaviest element in the periodic table, if I'm not mistaken, that is uranium. Based on my memory, just review that also. Uranium, I'm not sure, the heaviest element in the periodic table, or the heaviest element in the universe, something like that. Okay, correct me if I'm wrong, because that was 20 years ago. Okay, like that. But I am really sure that the most abundant element in the universe is oxygen. Something like that. Okay. And the lightest element in the universe is, I think, not so sure, hydrogen. Something like that. Because only one. Atomic weight is only one. There's zero. There's atomic zero. There's atomic weight zero. If there's an atomic weight zero in the periodic table, that is the lightest element in the universe. Periodic table at your hand now, the periodic table will not start at zero, right? The atomic number, it always starts with one. And number one there is the hydrogen, capital H. So it is understood that it's the lightest because the atomic number is zero. And atomic weight is only 1 point something. Okay? I think helium is 2. Because sometimes some students are confusing with helium also. Okay, helium, He, the gas involved in the balloon or the gas involved in scuba diving. Okay, there's helium there. Okay, like that. I think hydrogen, like that. So that is more on the periodic tables. I think we're gonna do that for my next live streaming. Next live. Okay, thank you. Oh my God, we're still number 4, right? It's just analyze number 4 directly because it's just the same, right? Like this. Okay, I let you solve for yourself the number 4. Okay, a reaction mixture initially contains of 0.25 molar of carbon monoxide. My gosh, comma. And 0.40 molar of oxygen gas. Okay. At equilibrium, the concentration of CO2 is 0.15. Calculate the equilibrium constant of the concentration. So our reaction will be CO plus oxygen gas, right? And then equal to CO2. We need to balance first this one. Okay. Let's just finish this one, huh? Okay. So take a look at the problem. Problem number 4. Okay. Like that. Okay. I think this is incomplete combustion. This is not complete combustion. Okay. Okay. Because as far as I could remember theoretically, if we add oxygen, meaning to say there's a rapid oxidation, so automatically our reaction there would be combustion process. In combustion process, there are 2 types. Starts with incomplete combustion and later part we have the complete combustion, meaning to say it starts with incomplete before it will become a complete combustion. So in complete combustion, the carbon monoxide will be always present there. So in the problem, it always a carbon monoxide, right? So this is gonna be an incomplete combustion plus oxygen, right? Okay, let's try the reaction because I doubt this is incomplete combustion. Yeah, here is water. You remember? We need to add oxygen in rapid oxidation for a certain hydrocarbons or any organic compound that contains CHOs. Okay, carbon element, hydrogen element, oxygen element. There must always be water plus carbon dioxide. But here, the product is only carbon dioxide. Where's water? It's lost. So that means this is an incomplete combustion, 100% sure. Okay, by theory. I hope the balancing will be okay. Gosh. My gosh, balance na naman. Okay. Carbon monoxide, CO siya, carbon monoxide is also a toxic gas and this is also deadly gas. Okay, the limit for the concentration that a person can be safely exposed to at 8 hours, the TLV is 45 ppm, parts per million. Something like that. Okay? 45 to 50, I think so, parts per million, the units of concentration, okay, parts per million. So parts of toxic contaminant per parts per million, but actually per million of carbon monoxide. So the contaminant in that carbon monoxide are being measured over to the CO as a whole. That's parts per million. Again, parts of air contaminant per million of carbon monoxide. So, in short, parts per million, like this. And that is a concentration. And the TLV, or the threshold limit value for carbon monoxide, is gonna be 45 to 50, something, the range will play around there. And we determine that one during our gas testing in different confined spaces, vessels, manholes, pipelines, or whatever, any vessels that has limited entry and exits, and there's a chance of atmospheric gases inside. Okay, like that. Carbon monoxide should be tested because this is one of the deadly and toxic gas. It can kill a person immediately, just like as the hydrogen sulfide H2S. These two are killer gases. Okay? So be careful with the incomplete combustion. This is a killer gas or a deadly gas, something like that. It will suffocate you. Also, for example, if your car is totally closed and you cannot escape, and there's a leak of the gas in the engine, in the internal engine of the car or vehicles have internal combustion engine in which the combustion process took place in that engine, and then if there's a leakage of the particular gas, an incomplete combustion will be there, and the carbon monoxide will escape there, and it will be surrounding inside the car. And if your car windows are totally closed, you will be suffocated, okay, and you will be losing oxygen in your system, and you will die because this carbon monoxide will eat all the oxygen inside your system, okay, and then you will die. So this is a killer gas and a deadly gas, carbon monoxide. Okay, so this is always involved in incomplete combustion process. Okay, that's a small theoretical aspects of carbon monoxide. Here, going back to the problem. So carbon monoxide plus oxygen gas is equal to, okay, let's just analyze. If CO2 is not given there, some students will answer this, the product will be CO3, right? Correct me if I'm wrong. Normally, majority of the students will predict the product as CO3, right? This one. CO3. Carbon monoxide plus oxygen gas equals to CO3, carbonate. Carbonate. But take note, oxygen are balanced immediately, right? 3. Carbon also 1. This is not correct. Why? Because CO is an incomplete combustion. During the complete combustion, somewhere along the way, it will release CO2. It's not CO3. That's the first theoretical aspect. Okay? Number 2, this CO3 will not exist alone in the product because this is a polyatomic ion. Okay? Polyatomic ions that has charges could either be negative, something like that, will not exist as a solo element during the product after the chemical reaction. Okay, this is not a standalone element because this is a polyatomic. There must be a partner for that. For example, H2CO3 or hydrocarbonic acid, hydrogen carbonic acid, something like that. Okay, calcium carbonate, like this, or the limestone. Okay, like that. Magnesium carbonate. Okay, like that. There must have a partner always in the product or in the reactant, but it is not a standalone carbonate in the chemical reaction, or else you will force to put that negative here. Okay, like that. But this is not redox oxidation number in the oxidation state that we are focused on the charges. It's not that, because this is a chemical equation. No need to stress out the charges during the writing of the chemical reaction. Very clear. So this is wrong. Okay, though it's balanced as you look at, but this is wrong. Because if you try to force this, you will put this -2 here. because carbonate has negative 2 charge, because this is a polyatomic ion. Okay? This is wrong. So we need to write again CO plus oxygen gas is equals to CO2. So this is the correct one. Okay, because this CO will produce CO2. Okay, now you balance this one. Okay. Now, in this equation, we need to avoid a fraction. Okay, like this. So oxygen 3, okay. So the oxygen is 2, okay. 2, so you can automatically put 2, okay, to carbon. Okay, like this. 2 carbon, oxygen 2, oxygen 4. Then we need to put 2 on the carbon, sorry. Okay, this is balance. Okay, you like this, right? This is what you like, that automatic, no need to let X, like the algebraic expression to get the number of, because you want direct like this. This is in the case you will use the direct, because if you use fraction, this will not hold through that much, because this is incomplete combustion. Okay? In fact, this is not a reversible reaction. This is irreversible reaction. I think so. Okay? Just analyze. Reversible reaction meaning if you try to invert the reaction, let's say this product will be reactant, it will produce the same product as this. That's a reversible. But irreversible, it will be longer like this if you reverse the equation. So that is reversible reaction and reversible reaction. Something like that. This is not reversible, okay? Because if you try to make this CO2 as a reactant, it will produce carbon and oxygen gas immediately. Like this. Okay? Yes. It's not reversible. It's irreversible, okay? But that's not our concern, huh? Our concern is to balance the equation. Okay? Balance. 2 carbon, oxygen is 4. Yes, balance. But let's try to adopt the more formal if we assume this is a complete combustion. Okay? Leave that one. I need to explain the usual law of conservation of mass balancing. This one. Because this is only a trial and error method. Because this is incomplete combustion. The fractional, atoms will not be applied here. Okay, so CO. Okay, it's equals to CO2, right? Carbon balance. Oh, carbon balance 1 1 blah blah so and so. Okay, oxygen is 3. Oxygen is 2. See? In our reactant, the oxygen 3 and our product's oxygen 2 is balanced, so the efficient is in the product. So we let X in the CO as our number of coefficient to make it balance with the other one. So X, charots. So 3 is equals to 2 oxygen times X. So X is equals to 3 halves. So we have now an atom that is fractional. Okay? In a law of conservation of mass. Okay? Oxygen 3, oxygen 2, and then we let 3 is equal to 2x because we assume the x of the coefficient of CO2. So x is equal to 3 halves. Okay? We put down the 3 halves, remove the x. Okay? Like this. So, CO plus oxygen gas is equals to 3 halves carbon dioxide. Now, we need to avoid fractional. We need to cancel the denominator 2. So, multiply that by 2. Okay? Like this. Both sides. Multiply by 2. So it will now become 2CO plus 2O2 plus 3CO2. So this is our chemical reaction. 2CO plus 2 oxygen gas, 3 CO2. Balance it. So oxygen is 4. Oxygen is 6, right? And then carbon is 2. And carbon here is 3. So it is not balanced. Okay? So rebalance again. Okay? So 2 carbon. My gosh. 3 carbon. So let this as X. So 2X. And then equals to 3. So X equals to 3 halves. For carbon, see? For carbon, we can get 3 halves. Okay? Like this. We balance again. Okay? Because this is not balanced. Balance again. Carbon. Okay? Carbon is equals to 2X equals to, by mathematics. Okay? 3 halves. Put the 3 halves here again. See? Very, So 3 halves times 2CO plus 2 oxygen gas is equals to 3CO2. Okay, like this. This is your equation now. 3 halves 2CO plus 2O2 is equals to 3CO2. No, this is equals, huh? Like this. 3CO2. Now, simplify that one further. Okay. Huwag yun akong papilan in fairness. Simplify further. We can have, if you simplify further here, by 2 is 3. So 3CO. Right? So 3CO plus 2O2 is equals to 3CO2. Okay? Balance again. Carbon 3, carbon 3, oxygen is 3 plus 4 is equals to 7, oxygen is equals to 6. See? I balance again. So oxygen lang is not balanced again. Okay? This is second balancing, huh? Okay, so what we will do now for this, so we'll let X to the deficient. So we have 6X in the CO2 here. Okay, not here, because here is 7, it's more. So 7 is equals to 6X. So X is equals to 7 over 6. Okay, 6 equals to 7 over 6. Substitute again that here. Okay, so 3CO plus 2 oxygen gas is equals to 7, 6, 3CO2. Like this. Okay, like that. Now, we need to cancel that out 6. Okay, so multiply by 6. Okay, we need to cancel the 7, 6 here. Okay, oh my gosh. Like this. See? So cancel. 6, 6. So 6 times 3, 18 CO plus 12 O2 plus 7. 7 times 3 is 21 CO2. This is our balancing now. So very big coefficients. Try to simplify that by using the least common denominator. If half, okay, let's say 3. So divided by 3 is 6CO, 4CO, 7CO2. So this is our final equation. 6CO plus 4CO is for 7CO2. And balance again. Carbon 6, carbon 7, okay. Oxygen is 6 plus 4, 10. Oxygen is 14. See? We have now our fourth balancing. As you can notice, how many balance we did? Fourth balance or fifth balance. Balancing the equation. So this will prove that the reaction given in the problem is an incomplete combustion. Even though how many times we will balance the chemical equation, it will never be balanced because this is an incomplete combustion. Okay? Like that. Okay. By using these theoretical aspects, the law of conservation of mass, it will never be correct to balance this CO plus oxygen gas equals to CO2. Okay? Now, if we just use the trial and error method like this, in which the most students love, okay, without employing the theory of the law of conservation of mass, by assigning only the trial and error method, it will be balanced. So 2 moles of CO plus oxygen gas is equals to 2 CO2. So it's very easy to balance by putting only 2. Okay? Like this. Okay, so we will use this one. Not the other one because it will never balance if you use this one. This is a trial and error balance. This is rare cases. Rare case because this carbon monoxide is always in the incomplete combustion. Okay? Take note. If you meet like this, incomplete combustion, why combustion? Because there's an oxygen gas. If you add something to a compound, to acidic solution or whatever, it will automatically be a rapid oxidation reaction in which combustion process. But this time, our carbon monoxide has no H, has no hydrogen. So this is not a hydrocarbon. That's why we cannot release water in the product. You know, if we cannot release water in the product during the combustion process, that means that is incomplete combustion. Because perfect combustion or complete combustion always have water in the product, carbon dioxide plus water. But in this case, even if we add oxygen gas to carbon monoxide, there's no water in the product because there's no presence of H element in the reactant we added with oxygen. Is carbon monoxide. There's no H in carbon monoxide. So you shouldn't expect water in the product. Common sense. Okay? So this is incomplete combustion really. Okay, so in this case, we don't need to abide the basic theory of law of conservation of mass. Follow the trial and error of balancing by putting any number as you want, as you like, as long as it will be balanced. This is what? Okay? Because we are not really sure. If we not put 2 here, we don't know what moles we will be able to put in order this to be balanced. So start with the most, starting from the most least number, 1, 2, 3, 4, 5, 6, 7. The technique is start with 2, right? So that's why upon putting 2, then it will be balanced. Okay? Like this. Okay? And then you will see also, why I put 2 on the product, not on the reactant. That's why it is a trial and error. You put first here in the product, and then let's say if it's balanced. And if it is not balanced, you will put 2 also in the carbon monoxide. If it is balanced, then no need to put 2 in the product. Okay, if it's not still balanced, then put 2 in oxygen gas also. So that is trial and error. Okay? Because this is an incomplete combustion without the presence of hydrogen ion. Okay, like that. Like this. So our equilibrium expression will be basing here. Okay? Like that. So this one, we will now substitute the equilibrium concentration. Oh my God, what's happening? Okay, I have to finish this one. Okay, KC, tarot. So basing on that equation that we use, no, right? This one, we will use this one, ha? This one. This one. We will use this one. Okay? In the KZ equilibrium constant expression because it's balanced by trial and error method. Okay? So like this. So KZ is equals to CO2 raised to the power 2 and then CO raised to the power 2 and oxygen gas. So this one. Okay. So this is our formula. Kc is equals to carbon dioxide raised to the power 2 because there's a number of moles of the carbon dioxide in the reaction. Okay, and then over carbon monoxide concentration raised to the power 2 because there's also 2 moles in CO. And then oxygen gas, there's no mole in the beside the oxygen gas, so there's no exponent. Like that. We compute for the Kz. Individually, we will substitute the equilibrium concentrations of CO2, CO, and O. Let's look at the problem if it's given. Number 4. Okay. Is there stating the equilibrium concentration? Okay. It's here. A reaction mixture initially contains of 25 molar CO and 45 molar CO2. At equilibrium, the concentration of CO2 is 0.15. Have, but only the CO2 is given in the equilibrium. CO2 is equals to 0.15 molar. Okay, at equilibrium. Capital E at equilibrium. Our concentration of CO2 is 0.15 molar. This is at equilibrium. So this CO2 will be automatically substituted to here already because it's an equilibrium expression. Our problem now is only the CO and the O2. Okay, we need to follow again the ICE method. Okay, 2CO, going back to the reaction, 2CO plus oxygen gas is equals to 2CO2. Okay, I initial. So in this problem, there's an initial. Okay, read it. A reaction mixture initially contains 0.25 molar of carbon monoxide and 0.40 molar of, what's this other one? Oxygen gas. So have initial, right? So carbon monoxide is 0.25. Okay, and a CO2 has no concentration initially, but the equilibrium concentration was given. Okay, it's different. Equilibrium concentration and initial concentration is different from the ICE method. Okay, let's put 0. And now we go to the changes, capital C. Okay, take a look on your reactant. Your reactant has 2 moles of carbon monoxide plus 1 mole of oxygen gas. So our changes will be 0.25 minus 2x because we multiply our x molar concentration to the number of moles. That's the principle behind. Molar concentration is equal to the number of moles multiply the x that we assume we able to get, or the molar concentration. So that is 0.25. Sorry, that is minus 2x pa. Okay. 2x pa ang inyong changes ha. Nagdali ko sa equilibrium. I'm getting fast with the equilibrium. Okay. Changes is only negative 2x. Okay. And then negative minus x for the oxygen. Oxygen is only minus x. And the CO carbon monoxide is minus 2x. So, coefficient or the number of moles times the x in which we are trying to assume to solve for, that is x molar concentration, plus 1 minus x only. Okay? Minus x, why? 1 times x. Minus x. Okay? Subscript is not included, huh? It's only the coefficient times the x. Okay? Like this. And our change in the 2CO2 will be positive 2x. Okay. Positive 2 is meaning this CO2 will receive the molar concentrations given by CO and O2. That's why positive. If we give negative, if we receive positive, just remember that one. Okay? Equilibrium, 0.25 minus 2x. Okay? 0.4 minus x. And then, this is only 2x. Okay? 0.25 minus 2x. And then, carbon monoxide. And then for oxygen gas, we have 0.4 minus x only because there's no number of moles on the oxygen gas. And then for the CO2 will be positive 2x. And then in equilibrium, the positive sign will be removed. This 2x because it's not necessary anymore. Okay? Like that. Okay? And then Kz. Here we will substitute now here like this in this equation. Okay. We will substitute this one by one. But take note, our equilibrium concentration of CO2 is 0.15 already. Okay? So, 2x is equals to 0.15. See? Our equilibrium concentration of what's this one? CO2 is 2x. So 2x is equals to 0.15 because this is the 2x is equals to 0.15, x is equals to 0.15 divided by 2. So we have now x as our molar concentration. So after getting x, it will be substituted to all x there and then all will be solved. Okay? Like this. .15 divided by 2 is equals to 0.075. Our x is 0.075. This one. We have now from here, we have now our x, which is 0.075, the molar concentration that we assume in order we can compute for the equilibrium concentrations of the products and reactants. Now, going back to the expressions of the equilibrium, and we have the value of x. Substitute that here, x here, this one 0.075 here, and this one 0.075 here also, and 2x here. We can get now each molar concentrations at equilibrium. Okay? Because capital E, at equilibrium, not on the changes, not on the initial. You have to identify the equilibrium concentration. So our clue here in the equilibrium problem, of course, the equilibrium concentrations. If given, well, you will be happy, something like that. If no given, you will be headache because too much solving. You will be going to the quadratic equation, blah blah blah, so and so, factoring method in algebra. But if it is having the equilibrium concentrations of the products and reactants, then it will be a happier times. Or else, if it's given all, you can substitute all, you can get the Kc. Okay, like this. So, substitute here, the x. Okay, ganun siya. Burot yun akong papel. In fairness, hello guys, are you still there watching my live stream regarding equilibrium dissociation of molecules? Okay, thank you so much for spending your time with me. Okay, my gosh. Okay, equilibrium. For CO, 0.25 minus 2 times x. 0.25 minus 2 times 0.0075 is equals to charots. 2 times 0.075 is equals to 0.15. So 0.25 minus 0.15. 0.25 minus 0.15, 0.1. molar for CO. And then for O2, 0.4 x, 0.4 minus 0.15, 0.400 minus 0.15, 0.25, 0.400 minus 0.15, 0.25. So O2, 0.25 molar. And then CO2, 2x. So 2 times 0.15, 2 times 0.15 is equals to 0.3 molar CO2. Okay, this one. You have now the molar concentrations in equilibrium that involves X. Focus on that equilibrium concentration in your ICE method. And then substitute the value of X in which that is 0.15. Okay, because 2x is equals to 0.15 because 0.15 is given in the equilibrium concentration of CO2 in the problem. Okay, substitute immediately there all the value of CO2, CO, and oxygen gas. We can obtain Kc, which is being asked in the problem. Okay, Kc is equals to CO2 C raised to the power 2 oxygen gas. So CO2 0.3 to CO 0.10 2 and 0.25. Now bingo, 0.3 times 0.3, 0.09, 0.10 times 0.10 times 0.55, 0.0025. So Kz is equals to 0.09 divided with 0.0025. Kz is 36. 0.09 divided by 0.0025 is equals to Kc is 36. So our this one, my gosh. See? Oh my gosh. Kc is equals to carbon dioxide to the power 2 over carbon monoxide is to the power 2 over times oxygen gas. Substitute the H values. So we have now Kc is equals to 36. Okay, our equilibrium constant concentration is 36. Okay, like that. Okay. So, thank you so much guys for listening and watching this live streaming regarding solving problems on equilibrium dissociation of molecules. So, just bear in mind that we need to use the ICE method. The first step is to have the chemical reactions, okay, predict the products like this, okay, and then balance the chemical equation and apply the ICE method, and then use the equilibrium constant expression formula, which is the concentration of the products over the concentration of the reactants, and then ensure that there are equilibrium concentrations given so that your headache will be reduced because it can be solved easily and faster if the equilibrium concentrations will be given. Okay, the initial way of doing that one will be the same, the changes will be the same, and it will follow through other problems. The only problem is the examiner will try to confuse the students by putting another variables which are not needed or relevant in solving what is being asked or required in that particular problem. Okay, so that is measuring the analysis and the comprehension of the students if they really understand, even if there are irrelevant variables, will be trying to incorporate it with particular problem, something like that. Okay, thank you so much. There are four problems, and I think you are enjoying also solving the problems. If you do, then cheers. Okay, like that. Okay, if you think and I did it, we done, we are done, right? Four problems in a row. Okay, if you think this live stream of this video, which is almost 2 hours plus, if you like this, then you can comment, you can like immediately, or you can share this video to your friends or to your loved ones so that we can share the little academic information regarding this topic. Okay, and you can even click the notification bell for some newest updates of Sotero. The coverage are science, mathematics, okay, occupational safety and health, music, entertainment, singing, like this. Okay, just go there in my YT channel and you will enjoy at least 227 videos all in all. There's a mixture also a little bit of singing because there's a problem of the copyright claims and I stopped uploading singing sessions and singing moments. I made my other YT channel I created. Okay, here is the other YT channel. You can also subscribe there and watch my videos there also. My title there is exclusive singing touch authentic vocalist. Okay, like that. That's my title of my other YT channel, and it's very unique. I think so. I think so. There's no similar title on that particular YT channel of mine in the whole universe. I check it out already because when you try to type that in YT, there's no similar that will appear on the screen if the audiences or the viewers will try to, type that. Okay, there's no similar with that kind of title. Okay, exclusive singing task authentic vocalist. Okay, like this. Okay, that's my other YT channel, exclusive for singing only. For now, momentarily, I'll just separate my singing sessions and my, theoretical discussions or academic information. Okay, I have two channels. Okay, but if you want to help me and to support me, just go over this channel because this is more informative compared to the other one because it's more on pleasure only, listening pleasures. Okay, using the talent and show to everybody. Okay, like this. But this one is more on academic information, very educational. Okay, if you have your children that are studying chemistry right now, then you can also help them a little bit. Okay, through this discussion, if you learn something new or you understand something, then you can share with them also, your children or your nieces, your nephews, like that, whatever, chuba chuchu. Okay, you can do that. Okay. Thank you so much. God bless everybody. Okay, see you later. Mwah. Babush.